We're finishing up a section on storms here. And we've talked about convective storms. That is air mass thunderstorms, severe thunderstorms. Oh, by the way, so I've been calling these things severe thunderstorms. When you're reading the book, notice they have subdivided that category into 3 or 4 smaller categories. You've got your squall lines and your mesoscale convective systems and so on. So just remember, again, they're going into this in somewhat more detail than I did in class. And then the third category we had was hurricanes, and we finished that up last time. But if there are any questions on these convective storms, this would be a time to bring other points out. Any questions about hurricanes that you've thought about since last time? No? Okay. Well then, the last category that we'll be doing is quite different. It's the mid-latitude frontal cyclone. And as I mentioned in the beginning of the section, this gets its energy source from a different place. All the convective storms get their energy from the release of latent heat as water vapor condenses to form liquid or ice, but not these. These come from horizontal temperature gradients. The point is that if you've got cold air next to warm air, there is potential energy there because the warm air wants to rise and the cold air wants to sink and spread underneath the warm air. So if I were to release, if I had a wall, for example, separating the warm air and the cold air, and I suddenly remove that wall, things would start to change. The warm air would rise up, the cold air would slump and slide under. So there is energy available when you've got these lateral temperature gradients, and that is the source of energy for frontal cyclones. So this name is a long one, but mid-latitude tells us where these things form. Frontal, a front is a boundary between cold and warm air. And of course, this is a little bit redundant because mid-latitudes is the region where you get the strongest contrast between cold air to the north and warm air to the south. So there's a little bit of redundancy here. But then it's a cyclone. It ends up being a counterclockwise circulation in the northern hemisphere, just like a hurricane, but the dynamics and the details are really quite different, even though they end up with a circulation around a low pressure center, just like a hurricane. They grow from a disturbance along the polar front. The polar front is this boundary that goes around the Earth in mid-latitude, separating cold from warm air. And when a little kink develops in that boundary, as I'll show you, it then grows and develops a frontal cyclone. Because they occur in the belt of westerlies, as they evolve and grow, they move from west to east. Not always directly from west to east, maybe with some angle, but generally they move from west to east. I don't think I've ever seen a frontal cyclone that went backwards, that moved towards the west as it developed. They all move east in some way. And eventually, so these storms do have a life cycle. They don't last forever. They start from a little kink in the polar front, they grow, and as I will show, once the warm air has all been lifted upwards, then the energy source is gone and these storms will begin to die. So they do have a natural life cycle. Typically, they last, 5 to 7 days as they move across the landscape from west to east. So here's a simple picture of one. It's got the classic features of the low pressure center, the cold front, and the warm front. And also scattered around the diagram are some of the indications of some of the types of local weather that you get. So I'll come back to define these fronts in just a minute. But first of all, you've got some rain showers along the cold front. In this case, you've got some freezing rain up here. Remember what causes that? That's that cold aloft, warm, and then cold near the surface that can supercool those raindrops before they hit the surface. And you've got light snow here, heavy snow back in the cold air. So a lot of local types of weather are going along with this large-scale storm. Now, in order to make any sense of frontal cyclones, you have to know the different definitions of the fronts. The word front by itself simply means a boundary between warm and cold air. A cold front, indicated by the filled triangles, is when the cold air is advancing. A warm front, indicated by the filled half circles, is when the warm air is advancing. So those little symbols are telling you how these fronts are moving. The cold air is back here, the warm air is there. So we know, because that's defined as a cold front, we know that it's moving in this direction. This one, the warm air is here, the cold air there. It's a warm front, so that means the warm air is advancing. It must be moving in that direction. So in a way, those are telling you a little bit about motion, how that front is moving with time. So that's and a few other definitions. So this little sector back here is called the warm sector. And of course, it has warm air moving up very often in New Haven. Very often that air is coming from the Caribbean. And behind it, you've got cold air, and usually that's coming down from Canada. So you end up with a contrast here across the cold front between air masses of different sources. Caribbean air here, Canadian air here. Notice also that this meets the criteria that I laid out a day or two ago about needing to transport heat northwards. So here's northward moving warm air, southward moving cold air. Probably the same amount of air altogether is moving, but there's a net transport of heat. Because you're pushing warm air northward and cold air southward, there's a net amount of heat being carried northward, and that helps to balance the excess solar radiation near the equator and the deficit of solar radiation and emitted radiation near the pole. So this plays a big role in the general circulation as well. Questions so far on frontal cyclone? So here's now is the history of one. It starts as a little dimple in the polar front. And already you can see the characteristics. The cold air begins to advance, so we can label that as a cold front. The warm air begins to push northward, so it can be labeled as a warm front. But it's very weak. A day or two later, it'll look more like this. This is a fully developed, mature cyclone. Low pressure center, cold front, warm sector, cold air come behind. Then it goes to this stage. This is called the early occlusion. And the word occlusion refers to the fact that now the cold fronts and the warm fronts, at least in the northern part, not here, but up here, they're beginning to come together. I want to try to describe that to you. And the main thing you have to recognize, I'll try to do it here on the table and hope you can see me. These fronts are drawn where they intersect the surface of the Earth, but they are not vertical boundaries in the atmosphere. They are tilted boundaries between cold and warm air. So for example, here's the cold front with cold air underneath the wedge. Here's the warm front with cold air underneath the wedge. And when they come together like this, now they're occluding because they have touched at the surface of the Earth. I'll lift it up and pretend the surface of the Earth is here. When they come together like this, now they are occluding. And notice that the warm air, which was in the middle, has been pinched off the ground. Now the warm air is up, and you've got cold air and cold air that have touched each other at the surface of the Earth. So that's the meaning of the word occlusion. It's where the cold front and the warm front have come together, pinching the warm air upwards. And that is where it wants to be, right? Warm air is buoyant, it wants to be up. So as soon as the occlusion begins, then the energy source to keep this storm going begins to weaken. This is the early occlusion, and now we can say cold front, warm front, and occluded front. Notice the symbols they're using. They put the warm front and the cold front together on the same side of the line, indicating that's now an occluded front. And here, it's occluded all the way down to there, and you've only got a little bit of the original cold and warm front. This one's, they've labeled it late occlusion. This storm is dying at this point. It's weakening due to friction and so on. The energy source is gone. Friction is acting to decay it. Typically, it'll take 5 to 7 days to go from this stage to that stage. And by that time, it's probably traveled 5,000 or 10,000 kilometers from west to east. This storm may have begun to form east of the Rocky Mountains, and it may finally occlude as it's approaching Greenland or even England. So these things travel a long distance while they are going through this kind of a life cycle. Questions on that? So this is another cartoon, but this one shows a little bit of that tilted structure. So here's the map view, north, south, east, west. There's the cold front, the warm sector. Now if I do a slice, a vertical slice through the atmosphere here, it's drawn at the bottom. There's the sloping cold front, and where it hits the ground is where it's marked on this map. There's the sloping warm front, and where it hits the ground is marked on the map there. And there are some characteristic cloud patterns that are connected with these fronts. Here, cirrus, cirrostratus, altostratus, nimbostratus. Nimbo means rain, and you see it's raining there. And these are generally stratus clouds out ahead of the warm front. The cold front, because you're lifting warmer air with more moisture in it, air that's in the warm sector, possibly air that's come up from the Caribbean, you tend to get more instability. That's a little cumulonimbus cloud there, or maybe in some cases it's stratus, nimbostratus and altocumulus, but these tend to be more unstable near the position of the cold front. And then cold air back here, warm and cold again here. But remember, because this is a cold front, not labeled here, but this is a cold front, it's moving in that direction. This is a warm front, which means it's moving in that direction also, towards the right in that diagram. So if we back out now and look at a larger piece of the northern hemisphere, on a typical day, anytime between now and next April, when you're getting strong temperature gradients north to south, this is typically what it looks like. So generally you've got the polar front wrapping all the way around the globe in mid-latitudes with a fairly strong temperature gradient across it. And then at different places it'll be doing different things. So on this little diagram you've got an occluded frontal cyclone here, you've got a mature one here, and one that's just starting out here, for example. And the fronts are labeled accordingly: cold front, warm front, stationary front, warm front, cold front, cold front, warm front, cold front, warm front, occluded front. So all the types of fronts are shown in this little cartoon. Question?
Is there a difference between an occluded and a stationary?
Yeah, a stationary front is, it's a definite cold-warm contrast, but it's not moving. Whereas an occluded front is a cold front and warm front that have come together. Therefore, you've got cold air on both sides, and the warm air has been lifted aloft. So there is a big difference. Notice that they are drawn differently. This has the symbols on opposite sides, where here the symbols are on the same side. So think about that. Maybe put a sketch in your notebook for these 4 types of fronts: cold front, warm front, stationary front, and occluded front. This is kind of the language by which we describe mid-latitude frontal cyclones. So this is the big weather producer. Throughout the fall, winter, and spring months in mid-latitudes, these things just come at us one after the other. Generally, they control the cycle of weather in mid-latitudes. You'll have a couple days of warm air blowing from the south. Some precipitation will follow. Then you'll have a couple days with cold air coming down from the north. So imagine this whole thing moving west to east while you are stationary. It's almost as if you are moving in the other direction, experiencing this and then this and then this as these things move over you. Unfortunately, they're not periodic. They don't happen with great periodicity, so it becomes rather difficult to predict the weather. But as you get into the cycle, if you begin to watch the weather every day and occasionally take a peek at a weather map, you'll begin to understand this cycle of events that is coming at you day after day, week after week, throughout the cool season of the year. Yes?
How can you tell by looking at it whether it's mature or in the early season?
Well, it's a little bit deeper, I guess. They've drawn that. I must admit that was kind of a judgment call. These two don't look so very different. This one was occluded, though, so I could see that this is in the final. These, maybe it was a judgment call as to whether this is more mature. It just looked like they'd drawn it a little bit deeper to me. And as I've discussed when we were talking about clouds, from space, these storms look like giant commas. And then once you see the comma, you can try to figure out where those fronts are. The cold front is probably down here. The center of the low pressure is somewhere in here. It almost has an eye in this case. The winds are going around this direction. The cold air from Canada is coming down in here. Warm air is blowing up there. The warm front might be back in here without much of an occluded front, or it might actually be this. Or, I'm sorry, it might actually be this, in which case this would be occluded all the way up there. So I can't tell for sure from that diagram where the warm front and the occluded front is, but it might be, I'm sure that's the cold front, but where the occlusion takes place, I'm not exactly sure. And the same thing over here. This is a different case altogether, but notice how similar they are. Low pressure center, probably an occluded front through here somewhere, and then these fronts will split apart. You'll have the warm front and the cold front. The cold air, when it comes down from Canada, notice how clear the sky is. When it comes over the ocean, that will be cold air over warm ocean, and you get this cumulus clouds building up over the ocean because you've suddenly heated that air from below, destabilizing the lapse rate, causing convection, and causing cumulus clouds to form. These aren't precipitating. These are precipitating. These are just cumulus clouds out over the ocean. Questions? So these are storms, and we need to know what they do. To a large extent, they are beneficial because they bring us the rain that we need and the snow up in the mountains that will then melt in the spring and summer and give us water in the rivers. But on the other hand, they can also bring damaging winds. Winds, especially on I'll tell you where the strong winds usually occur. Sometimes you get strong winds in the warm sector, but usually the strongest winds are back here, behind the cyclone, coming down from the northwest. And of course the rain, while it's needed, can sometimes be very heavy, or the snow can be very heavy, which can cause flooding or deep, impenetrable snow drifts. Because these storms do bring cold air down from the north, often they can cause very severe wind chill episodes with strong wind, sub-zero temperatures, and quite dangerous to be out in this kind of a storm. And then over the ocean, those strong winds mentioned here, winds passing over the ocean generate ocean waves. The stronger the winds, the bigger the waves, and they can be quite damaging to ships at sea. So these things have benefits but also dangers. I'll talk about a few of the famous ones in just a minute. Meteorologists like to put names on things. I think every field likes to put names on things. These are 4 typical storm tracks, directions where mid-latitude frontal cyclones tend to move fairly frequently. Ones that come in off the west coast, that were generated in the vicinity of Hawaii are sometimes referred to meteorologists as the Pineapple Express. Fun to use terms like that. Ones that come down from Canada are generated up in here and then come down towards the Midwest are often referred to as Alberta Clippers. We get a lot of storms in the West that were generated just east of the Rocky Mountains. We call those Rocky Mountain storms because of where they generated. But the most famous one from New England that you may have heard about is the nor'easter. How many have heard that term, nor'easter? All of you. So this is, it's just another mid-latitude cyclone, frontal cyclone, but it's called a nor'easter, and its characteristic is that it's normally generated in the northern part of the Gulf of Mexico, or more typically here along the coast, east coast of the United States, and then it moves up to New England from the south. Anybody know why they're called nor'easters? Well, okay, one answer is that they're traveling northeast. But remember, this is a traditional term. This term goes back 200 or 300 years before the motion of these storms was understood by anybody, right? Wind from the northeast. So if you are a New England fisherman or a farmer, especially a fisherman, and you're fishing offshore here, and the wind begins to pick up from the northeast, that is a sign that a storm is coming, and you would quickly head back to a sheltered cove or back to land to get your ship out of the storm. So a nor'easter is named nor'easter because the first sign of it in New England is the development of a northeasterly wind, an wind coming in from the northeast. Now, why is that unusual? Why would you notice that? Well, you're in the belt of westerlies here. So the winds are normally coming from west to east. So when a wind begins to blow from the northeast, well, that's a little bit different. And why is that a sign of a storm to come? Well, if a cyclone is coming at you from the south, remember the winds are coming around it this way. And so the first sign of it you will feel as it moves towards you is that easterly wind. You add a little bit of friction into that, and it's going to be a northeasterly wind. So the term nor'easter comes from the wind direction that is the first indication that this storm is approaching you. Is that clear? So, okay, nor'easter. Frontal cyclone approaching New England from the south. First sign is a strengthening wind from the northeast. There have been a lot of famous ones. I've just listed a few. There was a big blizzard in New England in 1888 that was, the storm of the century type thing that you can Google and find out about it. Soon after I moved to New Haven in 1978, there was a big blizzard. I remember we slept in our offices because we couldn't get home that night. There were drifting snow. And then recently there have been some, not quite as strong or as famous, but there have been some other nor'easters. And here's a typical satellite image. And Florida is covered here, but generally this is the east coast of the United States, and there's a big cyclone with the cold front, the occluded front, the warm front back into here, and that storm is moving up the coast from south to north, bringing all those different types of damages, the winds, the heavy rains, further enough north, heavy snow, maybe even some freezing rain up in the northeast. So all these different local things can happen. Yes?
How do the winds come from the northeast if the front is coming from the south?
Okay, lights on for a second here. So if I've got here's Florida, Cape Hatteras, Cape Cod, Long Island, New Haven. So there's a low pressure center here, let's say. Above the boundary layer where there's no friction, the isobar is going to be like this, and the winds are going to be traveling right around like that, paralleling the isobars. Down in the frictional boundary layer, where the winds aren't quite geostrophic, there's a little bit of a turning. They tend to move in, still generally going parallel to the isobars, but with a little bit of cross isobar flow as well. Now, so here you got some northeasterly winds, Now, as this storm moves up in this direction, and this pattern just translates. And so the first thing a fisherman up here feels is the wind blowing from the northeast, which is a sign that that's... So it's not the fronts that I'm talking about, it's the winds around that low pressure center that gives rise to the northeasterly winds as the first sign that this thing is approaching as it moves up the coast. Does that help? Other questions on this? So a lot of famous storms. The wreck of the Edmund Fitzgerald was a big tanker ship in the Great Lakes. And along came a frontal cyclone, you see it drawn here, back in 1975, developed waves so great on the Great Lakes that this ship broke apart and sank. Quite a thing at the time. And has anybody ever heard the song about that by Gordon Lightfoot? Google it. Listen to that song. It's a great song. It's kind of in there. It coincided with kind of the folk music era as well, and so this song became quite well known, describing this disaster, but also fitting into the genre of folk music at the time. So, very strong frontal cyclone generating waves on the Great Lakes. The blizzard of 1978, the one I mentioned here in New Haven, here's a satellite image of it. Now what you're seeing here, remember, are just the cumulus clouds as the cold air behind the cyclone comes out over the ocean. But these are the fronts back here, and very strong winds connected with that, and a lot of snowfall. And this is what the highways look like the next morning after the blizzard passed away. And then, have you heard of The Perfect Storm? This book by Sebastian Junger became quite a bestseller, describing a storm that hit the Grand Banks and sank a fisher boat, the Andrea Gale. And here's a picture of that storm. And notice it looks like the others. You've got the cold front, the warm front, the occluded front, the cyclone, strong winds and so on, producing big waves, and sunk that little. So you can read about that in Junger's book. Now, you get the same thing in the southern hemisphere, remember. In southern hemisphere winter, you get a big north-south temperature gradient, and you get mid-latitude frontal cyclones. They rotate in the opposite direction, just like hurricanes rotate oppositely in the southern hemisphere, so do mid-latitude frontal cyclones. They are, the winds spin clockwise around frontal cyclones in the southern hemisphere. And they are very strong down there, perhaps even stronger than in the northern hemisphere, which has given rise to these amusing terms for these latitude belts that you may have heard, the roaring 40s, the furious 50s, and even I've heard the term screaming 60s used, referring to these latitude belts where you get very intense and frequent mid-latitude frontal cyclones. And if you're sailing on a clipper ship 150 years ago out of England trying to reach somewhere, first of all, remember that the way you would do that, the winds down here are westerlies, just as they are in the northern hemisphere mid-latitude. So if you wanted to go to Australia, you'd come down here and then go east. And then if you wanted to return to England, you wouldn't try to go back against these. You'd go further east, and you'd come this way and then come back around. So here you have to go around Cape of Good Hope. Here you've got to go around Cape Horn, and especially Cape Horn is famous for all the shipwrecks that have occurred as ships have tried to go around through this belt of very intense and frequent mid-latitude frontal cyclones. So it's a very dangerous part of the world ocean in which to travel unless you've got a big ship. I've crossed that passage a couple times, and once or twice it's been fairly calm, and other times it's been anything but. Well, that's what I was going to say about frontal cyclones. Again, it's not as detailed as what the book goes into, but are there any questions at this point on frontal cyclones? Weather forecasting this is not a course in weather forecasting. You could take a whole course in this. But I want to say a few words about how one forecasts all these different types of storms, especially the mid-latitude frontal cyclones. It's pretty simple, but it's a big enterprise. So the way you do it is first to describe the initial state of the atmosphere. That is temperature, pressure, wind, humidity, everywhere, globally and vertically, at one time. You use weather balloons for that, surface stations, and satellites to get that state of the atmosphere described. Then you can use that as the initial condition on a giant integration of the equations of motion. These complicated equations, which you have seen simplified versions of in this course, like the perfect gas law, the hydrostatic equation, cloud processes, and so on, are all programmed into these equations, and then they're integrated forward. This is a huge job, and usually the largest supercomputers that exist in the world are dedicated to this problem. There are a few other defense applications that also have some of the world's biggest supercomputers, but for the most part, meteorology has led the way in the use of the biggest computer you could get, because it's a giant problem to compute forward in time the weather processes all around the globe. It all has to be done simultaneously. In this country, it's the National Weather Service that does all of that, collects the data and puts them into the equation and puts them into the computer and integrates those equations forward. And you can get your forecast direct from the Weather Service if you want, but then there's a big private sector industry that lies on top of that. They get the raw results from the computer output and then process it to make it useful for the consumer. They make pretty graphics, nice maps, predictions of what's going to happen hour by hour, build nice websites. You know some of the companies that do this. The Weather Channel is such a company. There's a company called AccuWeather that does this sort of thing. There's a half a dozen others that they don't do any of this work themselves. So actually it's a pretty sweet deal for these companies, because the government does all the hard work, and all they do is kind of pretty up the forecast, make it more useful for you and I, and then sell it to a television station or sell it to us or whatever in a nice, useful form. And then that whole process is repeated every 12 hours, right? That's why those balloons go up every 12 hours. That's the start of the next forecast cycle. So that's basically the way the forecast system works. People are always complaining about it's one of the burdens of being an atmospheric scientist. You sit down to somebody, next to somebody on a bus, and before you know it, they're complaining about how bad the weather forecasts are. You get a little bit tired of hearing that, because they're actually, for some purposes, they're not that bad. They're pretty good. Now, here's a diagram, okay, put out by the National Weather Service, so maybe a little bit biased, but no, it's very statistical. They define a skill score. I don't have the mathematical form of that to give you, but it's some kind of a measure of the quality of the forecast, how accurate the forecast was compared to what actually happened. And it's plotted on a scale from 0 to 80, but 100 would be a perfect forecast, perfect in all respects. This happens to be a forecast for the 500 millibar level. So it's not every aspect of the weather that's being presented here, just the shape of the isobaric patterns at 500 millibars. And starts in 1955 when weather forecasting first began using computers, and goes up to almost the present day. And let's follow the blue curve, which is the 36-hour forecast. So this is the skill of predicting the weather a day and a half in advance. Telling the future, if you like. What's the weather going to be, 36 hours in ahead. So the skill score was like 24 when it first started, and today it's something like 78. So whatever that, again, I haven't given you the formula by which that statistical measure is derived, but that's a pretty good improvement over the time. It's caused by two things: improvements in the numerical models and improvements in measuring that initial state. Both things are very important. Got to measure the initial state better, and you've got to have a more accurate model with higher spatial resolution too. Now, if you try to do a 72-hour forecast, 3-day forecast, of course your skill is going to be lower. The further out you go in the forecast, the worse is going to be the quality of your forecast. But that too has been improving. So today, the 72-hour forecast is about as good as the 36-hour forecast was in the early 80s. So we're definitely making progress on this. And of course, people are trying to compute out still further in time. If you go into the Weather Channel, you'll find forecasts out 7, 8, even 9 days in advance. I don't usually trust those, but they're fun to look at and speculate about what might be. Questions on this? So, for example, I've shown you some of these. This is a 500 millibar map from a couple days ago. It's this that they're basing that skill score on. Now that's a problem because you or I might be more interested in whether it's going to rain or not. But that's not what that particular skill score, there are others that measure that, but that particular skill score was just whether the correct prediction was made for the shape of those isobaric disturbances at 500 millibars. So I don't mean to claim that that measure of skill is all-encompassing. It just measures one aspect of weather forecasting. So here's my off-the-cuff summary about how well we're doing with various types of storms. With severe thunderstorms, we predict the probability pretty well. In other words, you'll hear a forecast saying something like 80% chance of thunderstorms tomorrow afternoon. We do that pretty well. But in terms of predicting when and where an individual storm is going to occur, we have almost no skill at that. We don't know whether it's going to occur over Hartford or Stamford. You just can't do that kind of local forecasting with this kind of storm because they're too chaotic, they're too random in what triggers them. Hurricanes, and the tornadoes, which come out of those, we're very poor at predicting when and where a tornado will arise. So we use what's called nowcasting. It's a funny term, almost a metaphor for failure, but it's a nowcasting means, as I showed you in the film the other day, nowcasting is seeing the thing and then saying, watch out. It's there. And also, it's not quite that bad because you could see it and see what direction it's moving. So you could give a few minutes warning to a community where that tornado is approaching. But in terms of being able to predict something like that from a numerical model, no, we have no skill at being able to predict from first principles when and where a tornado will occur. Moving on to hurricanes, genesis means when you first create the hurricane. We're very poor at that. Once the hurricane is formed, we're quite good at predicting where its track is going to be. That was, for example, Hurricane Irene was a good example of that. They really had that track nailed, even out 3 or 4 days in advance. They had a very good track forecast. As it changes its strength, however, as it moves along its track, it may weaken or strengthen. We're not very good at that. So certain things we do well. Frontal cyclones we're pretty good at. These wintertime storms, we often have good skill out to 5 days. Occasionally, we have a real bust. The Weather Service will fail to predict a big storm genesis event or will forecast one that didn't occur. But those busts are increasingly rare. And I'm amazed sometimes at how skillful the prediction of these storms can be out even several days in advance. Questions there? Now we won't finish this today, but I want you to start being aware of forecasts. I usually go to this page. So you can click to it on my website. It's the NCAR real-time weather data. And for example, right now, you could, well, let's look at the upper air data from 500 millibar sounding for this morning. This is the 12Z Friday sounding. You see it, the date and time up there. This is what the weather's doing right now at 500 millibars. This is a big trough in the west coast, a big ridge on the east coast, and then another cyclone moving away to the east. And this would be the starting point for integrations forward in time. And then if we go back, we can see what the forecast is going to be. I'll click on the forecast tab up here. And first of all, we could look over here. Here's the 12-hour forecast. So this is valid, 18 UTC Friday. So that's going to be valid in about 3 hours from now. And there's a nicely developed mid-latitude frontal cyclone down here, cold front, stationary front. Let's go forward in time. Let's go 36 hours in advance. So this is valid 12Z Saturday, so this is tomorrow morning at 8 a.m. You see what they're forecasting. The green gives you moisture and precipitation. The lows and the fronts are all there. So what about your New Haven weekend? It's not my job to give you indication of the forecast, but anyway, it's going to be a nice weekend, right? We've got a high pressure center over us. High pressure centers have descending air, cleans out the clouds, should be very nice for the weekend. And let's think about what's going to happen after that, however. So for now, I'm going to go to an animation. I think I want to animate this. Loop all times. We'll go to something like the 500 millibar winds, and we'll see if that's going to loop. Why isn't that looping? I didn't hit the loop there. Is that what I didn't do? Yeah, okay. So these are the forecasts now done from the recent balloon sounding as the initial condition. And you see that it's a very well-developed trough ridge system. And generally, the whole thing is creeping eastward. Now, this doesn't go very far forward in time. In fact, I don't know why. Did I not click on the right thing here? Loop all times. Yeah, well, it's only giving me a 12-hour forecast, which is not what I want. So let me try a different model. Yeah, okay. This one goes. This will be a different model. Same, yeah. Saturday, Sunday, still good weather over New Haven. Yeah. So remember, now this is a computer integration. This takes the balloon sounding satellite data for last Friday, for today, and then integrates it forward in time to get the forecast. And it may not be accurate towards the end of the time period, but it's probably pretty good for the next couple of days. We're out of time. We'll continue this on Monday.